Hello everyone, my name is Jongpil Yoon. I go by Joseph Yoon. Thank you very much for giving me opportunity to have a presentation at PLM conference in France. I'm currently a master's student majoring in industrial engineering at SKKU in South Korea. Talking about my research background, I've been studying digital twin, digital human, and smart manufacturing. The lab research I belong in is e-manufacturing, which is a field of manufacturing technology that enables smooth product development under cooperation system. The topics I'm going to cover is an applications of motion capture and haptic feedback wearable device for human-robot collaboration. Here's the contents. Consist of introduction, backgrounds, proposed method, implementation, and conclusions, and I'll go over step by step. Here's the introduction part. Many manufacturers believe that 4M, such as man, machine, material, and method, are the most important aspect in assembly task. Especially, humans are essential resource for manufacturing systems, but they are affected by many uncertainty factors. First, labor intensity, like material handling difficulty, is changing depends on durations of work and material weight. Second, proficiency can be varied from workers' experience. Third, human physical condition can be changeable day to day. Industry 4.0 has facilitated the automation and relies intelligent facility. However, this has led to major change in human workload as complex assembly lines still require manual labor and involves human errors. So unless eliminating manual process, human error is inevitable. Continuing introduction part, Industry 4.0 focus primarily on automation, whereas Industry 5.0 aims to combine advantage of human and robot through collaboration. Many researchers have been considering using collaborate robot to increase flexibility and responsiveness of production process. Robots have high physical strength and are sophisticated in terms of handling tasks, whereas humans are intelligent and have problem solving. Problems still exist in human-robot collaborations and listed below. First, human operators are still considered as a separator when robots were typically surrounded by a protective fence in a different zone. So physical separations will not utilize advantage of robot and human. Second problem is the presence of obstacle while using real-time camera may lead to a difficulty in creating virtual model for worker and robot. So in a situations, a worker turning his back and not showing his hand during interactions may put him in a dangerous situation. So the worker safety must be guaranteed during the interaction between human and robot in the same workspace. This paper proposed a framework enabling seamless collaboration between human and robot by increasing safety and accessibility. Three functionality allow the same workspace protect worker from severe accident. First, this indicates a collide body parts in the dashboard while human is wearing a haptic suit. Second, this application helps to avoid collision accidents by maintaining an appropriate safety distance from a robot surrounded by a virtual fence. Here is a research background explaining Operator 5.0 in smart manufacturing. Operator 4.0 is a smart and skilled operator who perform not only cooperate work with robots, but also work aided by machine. Operator 5.0 completes the Industry 5.0 requirements by adding resilience. So to fulfill Operator 5.0, there should be two types of resilience. First, self-resilience is a healthy, practical mind, spiritual and body approach that enhance how we deal with situations and challenges. In other meaning, it is a nature, physical, cognitive, and efficiency of operator which solely apply to a human. Second is a system resilience. In other meaning, it is a human-machine system to continue functioning by sharing control between human and robot to ensure performance and maintain system stability. Motion capture technology measures human posture and movements based on their position and orientation in 3D space. It also records information in a form that can use in a computer figure, digital human model. So you can see a man wearing a attire attached by multiple mocap sensor, and it will be configured in a digital humans in a virtual world. Digital human can track his motion simultaneously and create a digital representations of user. Haptic feedback creates an experience of touch by applying force and vibration. It also enables to interact with objects across the physical and virtual world. Tesla suit combines two electro-stimulations and has 68 haptic points. Talking about Tesla suit, it is based on sending tiny pulses of different amplitude, frequency, amperage to the electrode. The higher the density of points, the more accurate sensations the wearer will feel. Through the technology, user can form a non-verbal communication system. This is a framework I'm suggesting for human-robot collaborations. A worker wearing a Tesla suit enable motion capture, and haptic feedback will configure in a digital humans in digital world. At the same time, operator put a work order to control virtual robot in a virtual world. Two application services are provided through collision avoidance models. First is monitoring system. There are two functions involved here. Collision spot and warning message will be displayed in dashboard to visualize to supervisors, operators, worker. Second, full body tracking enable motion capture and haptic feedbacks to let user interact with other objects in the virtual world. By integrating these functions above, worker can feel haptic feedback response to his actions through electrostimulation. The loop keeps continuing until the movement is determined to be safe. So this is the first functionality I implemented for the application. Virtual fence will be installed at the end effectors of robots, and distance is measured from joint 2 to top of robot, and that becomes the safe distance, and it gets plugged into a volume of sphere, and creating a appropriate size of sphere virtual fence is very important. If it's too big, then it will be difficult for operator for seamless collaboration. If it's too small, safety is no longer guaranteed. The collision refers to a contact between digital human and virtual fence, not the actual robots or virtual robot. You can see 3 pictures, and in figure A, you might think that there is enough space between operators and robot. However, when a robot unexpectedly moves forward to worker, then that moment can be very dangerous and can put him in the severe accidents. So I installed a virtual fence at the end of the end effectors of robots, so it will prevent the robot's movement move further. Since there are many cases worker can be collide, so I designated 9 points on the operator side and 1 designated points for robot side. And 2 vectors are measured for the safety distance calculations through Euclidean distance equation. And 9 body parts are on a human's head, neck, both of his shoulder, elbow, and his hands and torso. And 1 designated point is at end effectors of robot. Here is the dashboard I implemented for better visualizations. Figure A shows workers' name, types of robots, and work order, and real-time distance calculations and number of collision, and also show the collision part where it got collide. And figure B shows the collide spots on the body, and it will be marked in red. This slide shows the development involvement, and the applications was implemented with a Windows OS because Windows 10 was suitable for Unity development. Unity 2020 and Visual Studio 2019 were adopted for to provide because it provides a high-level API with a C# language, which enable transfer motion data in real time. Tesla Suit, which is a wearable device, was used for interactions in virtual world, which enable motion capture and haptic feedback. Here is a video of showing me and our virtual humans interacting with robot. And you can see robots moves with disturbance and without disturbance. As you can see the video, robots can move upside down smoothly without disturbance. Whenever operator put his arms under, robot recognize as a disturbance and move backwards simultaneously. Here's another video showing a virtual robot and humans interacting in a manufacturing plant. As I mentioned earlier, dashboard shows the work orders and general information that can be useful for supervisors and operators, workers. And you can see the collision spots will be shown in a red mark. So body parts where it got collide will be marked in red. And similar scenario, robot moves upside down without disturbance. When he put his arms under, then it will show in red marks. And show the body parts where it got collide as well. Let me wrap up in a conclusion. I'm proposing a framework for seamless and safe human-robot interaction. So workers wearing a Tesla suit will create in a digital human. This can measure the risk and detect potential collisions in the interactions. These applications enable operator design collaborate robot process and train workers in a virtual world. In the future, I would like to connect the actual robot to the application and check to see if the assembly sequence is safe. Also, using reinforced learning algorithm will help to achieve automatic robot movement in the future. Thank you very much for paying attention to my presentation. I hope this paper helped speed up the arrivals of Industry 5.0. Thank you very much.
Thank you for your presentation. So any questions from the audience? Wait a second.
Yes, thank you for this presentation. When you say that the trajectory of the robot is updated according to the position of the joints of the user, what if the user move faster than the capacity of the robot?
So there are two methods to avoid the collisions. Either robots or humans avoid in a head. So let's say there is a collision, then this is the design process. So either robots can move that collisions to end, so it can detour the movements to avoid collisions, or human can move his movements. So either side can be eligible.
Okay, does the haptical feedback from the Tesla suit?
Yeah. So like I said, are you asking if haptic feedback is received for operators at the same time? Yes. So whenever there is collisions, the red mark will be shown, and that's indicate the collisions happened. And it will be, the numbers of collisions will be counted. Yeah.
Thank you.
Thank you.
Any further question? Frederic?
Okay, thank you very much for your presentation. How do you plan to combine the real robot with a virtual world? Because what you do currently is in a virtual world. If you try to connect, as you said in your conclusion, the physical robot to the virtual robot, what will be the objective for the real operator and the virtual or the operator in the immersive environment? That's not so clear for me. How you will organize all the collaboration between the virtual space, the real space, with a real operator or an operator in the virtual environment.
So you can see both of a physical world and virtual world. At this moment, physical robot is not exist. So in the future, I would like to connect real robot to the applications. You can, in the real robot, if operators interacting with physical robots, that can be they can put him in a dangerous situations. So I wanted to test multiple times in virtual world. So an operator can practice as much as he can to get used to it in the sequence process. So these applications allow user to design the sequence process and also train the movements. So once he finish the practice or if he get used to it, then the safety is guaranteed from my perspective. Thank you very much for your questions.
So maybe I have another question as well in that direction. You said that the suit has kind of a feedback.
Yes, sir.
But actually, you know, it's more the sensors that detect the distance between the robot and the arm or the torso whatsoever. So, you know, so you need more or less, you need the sensors, but not really the feedback.
Yes, so haptic feedback is implemented through Tesla suit because it can allow the non-verbal communication between robots and human.
So in order to stimulate the training process then better, or?
Yeah, training process and designing process. Both process can be utilized through this application.
Okay.
So thank you for the presentation. I was interested in. I had a question, so a bit in the same theme that the first one. If we admit that maybe someone is pushed on the robot and he can't dodge it because is fixed on the ground. So he had the procedure. I mean, maybe where he left his arm up to not damage the human. But if the suit then is damaged and the captors doesn't function, is there a risk that is repeating his movement, thinking that there's no danger anymore? So is there a procedure to stop the robot and maybe manually restarting it?
Yeah, so that can be happen in a design process. So until the movement is determined to be safe, the multiple times of designing between human and robot is needed. So just for your better understanding, the numbers of counted here is 21, but that can be realistic in real life. So honestly, you have to repeat multiple times until the number of collisions becomes 0. That's my point for this study. Thank you.
Okay, there's another question out there.
Hello, thank you very much for your presentation. I have a little question. When you say the robot is creating another trajectory, how is it is happen, or the robot is just reacting to the collision between the user and the collider that you put on the final effector of the robot?
So here for this study, this only shows the demo. So like a complicated movements pick and place of products is not showing, so it may not be realistic at this moment, but I can control through ROS system in the future to let robot pick the product from place to place, and at the same time, so all operators can interrupt their in same space, same workspace. So I hope this answered your questions. Let me know if I didn't still answer.
My question was with the collision that you put in the virtual system, the robot is just stopping because there is another
Yes.
collider. There is one collider, but the robot is not generating a new trajectory to avoid
Mm-hmm.
to don't hit the operator.
Mm-hmm. So you might saying the video right here, robots stop its movements whenever disturbance happens, and this you can't see, it's invisible, but a virtual fence is installed at end effectors of robots, so the robot cannot no longer go down because of a virtual fence. Does that answering your questions?
Yeah, thank you very much.
Thank you.
Okay, so thank you once again then for your presentation, and the next one hopefully is there and can prepare for his presentation. Thank you once again. So we have the next presentation on tele-existence interface for remote control of a physical industrial robot via data distribution service.
Okay. Oh, thank you.
Okay, so floor is yours.
Okay, so hello everyone. I'm Damien. I'm a PhD student at Cranfield University, and in the previous presentation we just saw a simulation to interact with a robot, and in my presentation I will propose an architecture to collaborate with the robot, but with the physical robot this time. So my paper is about a tele-existence interface for the remote control of a physical robot via data distribution service. My project is funded by the Anglo-French PhD scheme, with DSTL acting as a technical partner. So DSTL is the Defense Science and Technology Laboratory in the UK. So let's begin with a bit of the research background. In many sectors, work environment can be hazardous, such as nuclear engineering, manufacturing, or defense. Operators have to deal with heavy equipment, fast-moving machinery, or harmful material. Moreover, automation, the main objective of automation is to provide the highest level autonomy for complex and repetitive tasks. However, under unpredicted situation, automation finds limitation. Some of the existing industrial robots doesn't provide a turnkey solution to interact and collaborate with humans, and they usually require extensive training. And the reason of this is because the human-machine interface is not easy to use. So I'm proposing to use tele-existence for remote work. For the remote work, and tele-existence have the opportunity to enhance capability of way of working by providing new way of visualization and enable interaction in a simulated environment, immersive also. So to talk about the definition, teleexistence literally mean teleexistence, so virtual existence in a remote place. It is a concept first introduced by Professor Tashi in 1980 and defined by himself as a general technology that allows a human being to experience a real-time sensation of being in a place other than his actual location and interact with the remote environment, which may be real or virtual or a combination of both. So when we talk about teleexistence, it's usually linked with telepresence robot. So telepresence robot is what you can see, is this kind of audio-visual robot on the right, or video conferencing tool like Teams or Skype. However, teleexistence have a broader scope. And teleexistence aim to provide sense of existence in the virtual environment, or in the real world, either directly or through the virtual environment. And this is achieved by using a robotic system and sensor. Any kind of robotic system. It can be a 3-axis, 6-axis, aerial, ground robot, or humanoid robot if you want. It will depend on the use case. I did a comparative analysis of the different machine-to-machine protocol, included OPC UI, MQTT, and the one that came out and was filling my need of building a real-time distributed system was a data distribution service, DDS, which is a standard by Object Management Group, and which refers to the middleware networking protocol that aim to enable dependable, high-performance, interoperable, high real-time and scalable data exchanges using a publish-subscribe pattern. The reason I choose DDS, it is a data-centric protocol, which means for a developer, the developer have to deal only with the data and not where to get the data. It has an automated discovery process by which you can discover peers. It is transport independent, which means within the same system you can develop nodes on the same computer and use a shared memory to exchange the data, or you can use a wider local network and use UDP to exchange the data. And finally, it has a rich set of quality of service options, by which you can manage your system and performance of your system, how the data is received, how the data is sent. So the research question is, can a teleexistence-based interface can be applied to an industrial robotic arm using DDS and the immersive visualization of its digital twin? And I'm doing this work because there is a need to bring human operator and industrial robot. I'm not talking about collaborative robot, industrial robot, in the same collaborative environment when working remotely. So this research aims to present an efficient architecture using DDS and implement teleexistence, sense of presence in the remote environment. My contributions are the way of building a teleexistence interface using a game engine, Unity. I'm explaining why I'm choosing DDS protocol to support immersive remote control of the robot, and I illustrate the feasibility of the proposed architecture with a use case. So my architecture is organized as follows. In the robot operating environment, I've developed a gateway application in C# that communicating with the robot. And also I'm collecting data from 2 RGBD sensors. And on the remote operating location, I have my Unity immersive interface that collecting user input and displaying the environment thanks to a VR HMD. To give you a bit more detail about the system, on how DDS work. There is a data writer that publish data to a topic, and in the remote location, if the topic match and the sample match, then the data reader can subscribe to the data and receive the data. I have created my own custom topic and data structure. So this is example of data structure. For example, to monitor the robot, I have the robot state data structure to collect angle of the robot and effector position of the robot. I have the structure for the point cloud, the structure for the image, to collect the memory sequence and the image data, and also other structure to interact with the robot, so to choose which program I should launch and where the robot should go. According to Bowman, there is 3 different groups when you design a 3D user interface. So they are classified in navigation, selection and manipulation, and system control. So I have proposed my own way of interacting, manipulating, and control the system. There is plenty of other method, and each method should be evaluated to find the best way to provide a sense of existence in the remote environment. And there is also essential function when you operate a robot. So, for example, jog the robot, so moving the robot, register a new pose, switch between program, abort the current motion of the robot in case something happens, and reset the robot. So this is an example, for example, the 3D button that allow me to change the program and reset the robot and shut down the robot. I have also on the right some data information that is streamed in real time from the robot. And so this is the 2D viewer from the remote location. It's a general view of what is happening in the robot location. And the 3D point cloud, so 3D data streamed from the remote location. For my case study, I've used a robot available at Cranfield University, which is on the campus, but not at the same location where I'm operating the robot. So it is a Fanuc M20IA, which is surrounded by fence. So you cannot operate the robot if you are close to it. I've presetting a safety limit to not crash everything, and I've tested my DDS architecture over the Cranfield University network. I've used a VR HMD, and I didn't touch any hardware of the robot, but I've added 2 sensors, 2 RGBD sensors, so in this case, the Azure Kinect. I was talking about one feature of the DDS protocol is the quality of service. So in this case, I've been using best effort reliability QoS, which is good to stream data, because if a sample is lost, the system don't care and he keep updating the sample. So if there is a fault in the network layer, or the network is not constant, it's not a problem, because it will update the latest sample and without taking care of the previous one. So it's good to stream sensor data. Okay, so this is the framework demo finish. So as you can see, you have the digital shadow of the real robot, and you have, to operate the robot, you need to interact with this green end effector, which represents the pneumatic gripper of the Fanuc robot. So when the robot, the 3D cursor is green, the robot can reach the position, and when it is red, it cannot reach the position. So it's a bit laggy. And yeah, the robot is checking if the position is reachable before going there. So it doesn't collide with anything inside. I had a few technical issues. The first one is latency. When I receive the streamed data, there is no latency. There is a latency when I register new pose in the robotic controller. There is about half a second latency to register the data into the robot registry and update the program. Another technical issue I had is the coordinate system of Unity and the FANUC in my case are not the same. So I had the FANUC robot use XYZ in millimeter and WPR angle in degree. So I had to convert this pose into the game engine Unity a quaternion. So I'm doing this pose into a quaternion, but also a quaternion into the FANUC pose in order to have the good rotation and position. One of the limitations is open source software and commercial solutions are not well developed. So, for example, the FANUC SDK is only available on Windows, not on Linux. And if I would like to use the robotic operating system, there is no official package developed for FANUC, but it's the same for any industrial robot, KUKA, ABB. So where we could use this existence framework in the product lifecycle when the digital twin and the physical twin are available. The existence framework can offer a new way of interacting in the remote place by providing sense of presence for the operator. So to conclude this presentation, most of the robot simulation are stick with simulation. So I have proposed an architecture with a physical industrial robot that enhances visualization and aim to provide sense of presence in the remote location and intuitive interaction. My framework allows a human operator to interact with a normally fenced robot and collaborate with it. It speeds up the handling of the robot because the way of interacting are more natural. It uses immersive reality. And it's in the safe, immersive environment. For the further work, I would like to apply this architecture and this framework to remote NDT inspection, so under maintenance context. And what I'm doing right now is I'm evaluating the influence of all the interaction methods you have. So the different UI elements I show you and the different way of interacting, for example, with hand, with a voice command, how all of this impacts the sense of presence for the operator. And I also need to perform a long distance test and port network also use case. Thank you.
Okay, thank you, Damien, for your presentation. Any questions from the audience? Microphone is on its way. So do you have any industrial use cases in your first period of the project also involved?
So far it was only focused on the architecture, and now I'm applying this architecture into maintenance context, so visual inspection and thermography inspection.
Mm-hmm. Okay. So what kind of industry? In aviation or?
My PhD sponsor is in defense, so
Defense, okay.
defense.
Meanwhile, any questions? Okay, that's not the case. Thanks once again for your presentation.
Thank you.
And we come to the next presenter. Jan-Luca Siewert from my research group is presenting on augmented reality assisted quality control based on asset administration shell for concrete elements. Okay, should work quite soon.
All right, thanks for the introduction. My name is Jan-Luca Siebert from the Ruhr University in Bochum, and I'd like to present our AR-based quality control application that is built on the asset administration shell concept together with our co-authors Mario Wolf, Oliver Vogt, and Detlef Gerhardt. So this research is embedded into a larger research project that tries to build a fully digitalized flow production of precast concrete elements. So we're coming from, this project is from the building industry, and there we want to record and make available all the data, both from planning, from the building information modeling models that are available there, and of the actual production of these precast elements, and make all of them available. Either these data comes from the production itself, or as I said, from pre-existing building information management models. In the project, we chose the asset administration shell as an exchange format through the whole life cycle of this building. And our AR application for this quality control process should be an exemplary system where we show how we can use the data stored within this asset administration shells for other more sophisticated systems. The asset administration shell was already introduced this morning during the second keynote a little bit, but I'd like to highlight a few of the properties and a little bit of the concept behind the asset administration shell, just so you can all understand where or from which idea this project comes from. So the AAS aims to be the data model for IoT. So we want to represent every asset, both digital asset and physical assets, in the digital world by its asset administration shell. That means that we want to make all the data available there. And to structure that a little bit, we further divide an asset administration shell in so-called submodels. This means we can bundle information based from the domain where the data is coming from, or maybe for the application that is supposed to use this data. Both the asset administration shell and individual submodels are identifiable with globally unique identifiers. This allows us to reference different AAS and different submodels. And we can build more sophisticated networks. For example, we can have an asset administration shell for our production system and asset administration shell for individual parts or production lines or robots, or the assets that are being produced, and we can reference them each other to show this network of data. The asset administration shell should work along the whole life cycle of the product. So during planning, production, and operation. During planning, for example, with these concrete elements, we describe the type, and all of the assets that are being produced from this type share a lot of information. And this is then stored in a so-called type AAS, and during production, we can build instance AAS from that. So a little bit like object-oriented programming, where we have classes and objects, we have types and instances for an AAS. As mentioned this morning, these submodels are often used from existing specification, like for example, E-class, and then contain the actual data that can be individual properties, so values, but also collections of data, files that can either be stored directly in an AAS or more commonly are referenced and stored in an external repository. And then we have the existing standards like E-class, so we don't want to build all these submodels and all these properties by ourselves, but reference existing standards wherever possible. So we can link, for example, a property like a width or maybe an electric voltage, as heard in the keynote, and then reference the E-class describing this property, so everyone using the asset administration shell knows how to understand and interpret the data that is stored there. And then the AAS is supposed to be an exchange format between partners across the value chain, and on the other hand, also a communication protocol for the assets. So how does that work? The AAS is an exchange across value chain partners. Here on the left, we have the AAS from the point of view of the supplier. So as I said, he works with these types AAS on the top left here, and then creates instances of the product and instances of the AAS during production, and can then ship not only the product, but also the AAS describing these types and the actual asset to, for example, an integrator who can then use this exchange format so that he can import all the relevant data for an asset into his own, for example, IoT tools and rebuild this composite type machine in his own AAS repository. But that's only one side of the AAS. That's the type 1 AAS here, so passive AAS. So it's just a static file describing the properties of an asset. The next step are so-called reactive AAS, and that's what we use during our application here. So the asset administration shell doesn't remain static, but provides an API for other systems to access individual submodels and individual properties and update them and use them. The final step are so-called proactive AAS, where the individual assets can communicate through an Industry 4.0 language, but that isn't the focus of the talk here. So how do we apply the AAS concept for our flow production? We have on the physical world 3 parts that are of interest to us. That is first the production system producing the concrete elements, these precast elements themselves that are produced, and the quality control. And for our digital twin implementation, like we heard yesterday and today, we of course start with the system analysis before we go to process and data modeling and the interaction concepts to build a network of AAS, both for the production machines, for the actual precast elements, and for the individual sensors during our quality control. When we have a building, we can then further subdivide and describe the whole building through various asset administration shells. So we have an asset administration shell describing the whole building. We have asset administration shells for the individual stories in the building. And then we have these precast elements. These are typically corner elements, beam elements, or junction elements. And each and every one of them is described by an asset administration shell containing of an header where these identifiers are basically stored so that we can globally identify every single building, story, and element which in a building. And then we have the actual data in the body separated into individual submodels for the geometric definition, for example, with length, width, or material of the concrete element. We have the quality requirements and the actual quality assurance process that was performed. Quality control for concrete elements. I don't want to go into too much detail in this ontology. You can check the paper for that. The most important point here is that we have inspection tasks that we can define and separate that into individual actions that have to be performed. So we can build a simple checklist that the operator has to do during the quality control. And then when he has the results, we can evaluate the results and always reference the regulatory constraints that we maybe have for this specific element. The quality control itself can then be performed either manually or through inspection devices like a laser or a CT scanner. So how does our concept now look? So we start on the top with this BIM model where we actually describe all the individual concrete elements of our building. From there, we can export in an export format the asset administration shells for each and every of the concrete elements within our building. Furthermore, still within the BIM model, we can create and define these quality control tasks. So we select, for example, specific dimensions or faces that have to be checked later, and this data is then again exported into a specific submodel describing the quality control tasks that the operator should do. The actual AR tool can then download all this AAS for the specific asset that is to be checked, has an AR-ready quality control work plan available, and help the operator with simple visualizations and hints. And afterwards, the evaluation takes place, and the important part here is that the results of the quality control steps are then again stored within the asset administration shell, so that the results can be made available for systems that come later in the product lifecycle, for example, the actual assembly. What we then did is create a data model for this quality control. And again, check the paper for the details. The most important part is that we created two submodels holding all the information. That is, on the one hand, the geometric definition of the element we want to check. So we have the individual edges and faces and vertices that make up this element. And on the other hand, we have the quality control that is then again separated into individual tasks and individual actions that can contain, for example, the checking of a single dimension, or for example, an angle or flatness parameters. As I said, we start in building information management models, for example, in the screenshot of the BIM model here on the top. And then the user, when he prepares the asset administration shell, he can select an individual wall element and export an XML or a JSON file that is ready to be imported into the asset administration shell. The nice thing about these BIM models here is that all individual elements, so every face, every window, every door, but also the individual edges, already have globally unique identifiers attached to them. So the data format is well suited to be exported into an AAS later, because we can still maintain these references. So when we have an AAS with a specific ID, we can then check that with the BIM model and connect the data there. The actual augmented reality application has a simple flow here. So in the AR application, the user logs in, so we know who is performing the quality control tasks. The user then selects the AAS from our registry. We used Eclipse Basics as a registry, and we check if those two submodels we define that are relevant to our application are present, and if so, the user can select and download the content of the AAS. As I said, the content can be other AAS that are referenced or submodels, but also linked documents. For the AR part, the AAS also stores all information necessary to establish AR tracking. So for example, the point cloud of individual elements, so that we can later overlay the information in AR. That is done during the quality control steps. So we combine the tracking configuration together with the geometric definition and the quality control definition to show AR guidance to the operator. And afterwards, we dynamically update the values that were collected during the quality control and store them in the asset administration shell. So I have a few screenshots of our prototype. Here is just the browsing of the asset administration shell. So it's downloaded from our basics instance, and the user can then just scroll and select individual elements or individual submodels and see the links, the properties, the links to existing E-classes or other standards, so you can get an overview of the actual part. You can also, or we also create a tessellated version that is suitable for 3D visualization, like here. So this is the same wall element we've seen in the BIM model, exported as a tessellated, I think, OBJ file that the user can view. And if the user selects the actual inspection task, the application recognizes the special format of our submodel and can launch an augmented reality helper that helps him perform the actual quality control. This is just a simple validation of our data model. So we have just a 3D printed version of this wall element here, but you can still see how we dynamically use the data, dynamically identify the edge that the user should check, and can help the user perform the actual quality control. And as I said, all this information necessary, for example, the point clouds, are also stored in the AAS so that we can simply change, for example, the geometry, and the application can still work as expected. So what have we done? We've built a data format for this AR quality control based on the geometric definition of our concrete elements, built on the asset administration shell, and build this simple AR support application that is able to consume the data and produce data and update data within the AAS, and have shown how the asset administration shell can serve as an exchange format for different applications across the lifecycle. As you've seen, we have only a simple AR visualization with this 3D printed part. So the next step is to use this application during the actual flow production. Of course, the models and the concrete elements are way bigger than what I've shown you in the screenshot. So we want to change our AR tracking approach to one with a static camera that observes the production flow, then calculates the model tracking and overlays, and then wirelessly sends all this data to the mobile operator that can then wear a tablet or an edge-mounted display and can either just show the camera feed of this static camera together with AR overlay, or calculates the overlays itself by using the tracking information provided to them by the static setup. So thank you very much, and yeah, I welcome if some of you have any questions.
Thank you, Gianluca. So any questions from the audience? Over there.
Thanks for the presentation. You speak about digital twin, and I wanted to know what is the relation between the asset administration shell and the twinning process. Do you have any assumption and things to say about that?
Yeah, thanks for the question. We've already seen that digital twin is like the buzzword that is interpreted differently by other people. What we observe in the building and industry and civil engineering is often that the BIM model itself is the digital twin. It contains the geometric definition of the building, and for a lot of civil engineers, that is the digital twin of a building, the BIM model. We want to combine that with the digital twins and of the production process and the individual element, and that's why we chose the asset administration shell. At least in theory, or from a concept point of view, this AAS format aims to be the foundation of digital twins by describing all assets, connecting assets, referencing each other, and then maybe store additional, for example, simulation models and reference them from the AAS. So that's why why I have spoken from the digital twin of the individual asset there. I hope that answers the question.
Okay, any further questions? Maybe in addition to what was just said about the digital twin, in the production system, there's kind of an interaction when the product is produced. So the product can interact with the production system itself. Both can be represented by a digital twin. And so we have, let's say the digital twin representation in different phases of the life cycle. So one is already in production, one is just, getting produced, but might be then also part of a, let's say, bigger artifact that is represented by a digital twin for further, let's say, inspection process or whatever. Yeah. The concept itself is quite, let's say, general or quite generic. Okay, no more questions. So thanks once again then. And we come to the last presentation of this session, which is going to be held, I think, by Dimitris. No? No? So there was supposed to be the presentation about design and development of a G-code generator for CNC machine tools based on augmented reality, AR. So a no-show. Unfortunately, I'm not able to hold the presentation for that one. So we could discuss more on the... I think he's online. He's online? It's at least not indicated here, but I can, or maybe somebody can assist me and check if he's online. Dimitris Moutsis.
Nope, no one in the...
No one in the queue. I mean, we are a little bit ahead of schedule, as our 10 minutes ahead of schedule, but...
Comment?
There is a web page with the link of the people who should present online. Tu connais?
Non.
Nous avons envoyé des liens.
Okay, so we check,
Yeah.
check, recheck again.
I need to check that. T'es sûr qu'il est dans cette session? Je crois pas.
Ben là on est dans la session Barbillion. Hein. Il n'y a pas de raison en tout cas. Et il n'y a que Sébastien Martin. Hein.
What's his name?
Dimitris.
Because I received an email from Nikos Panopoulos.
He might be, yes, also one.
Yes, they are the same.
Yeah.
He's asking for the... on peut lui envoyer le lien là.
So maybe try to connect.
Invité.
Inviter qui?
Bah tu vais copier l'invitation.
Ok.
Ouais, c'est ça.
Yeah, it was not indicated. Here was a mail. Ah, okay. Yeah. So thanks to the other guys that we saved some 10 minutes. So
C'est où
Yeah.
Zimbra là?
can keep track.
C'est ça. Comment on accède aux mails?
Tu connais l'adresse pour les mails là?
Moi je vais toujours sur le site de GI, après je fais webmail, genre un service. Non mais prends genre décembre.
C'est lui là.
Bah tente là, ça il a l'air pas mal. C'est les nouveaux, je sais pas si c'est... Non, c'est celui de ton TCE. Ah merde, c'est pas lui. Prends lui.
Ok.
Ouais, ouais, c'est ça. Et après, moi, je fais nos sites, je prends Grenoble INP, n'importe. Ouais. Et là, tu fais e-service, webmail personnel.
So you didn't have the link for the Zoom conference?
I guess yes, because the links are in the website page, so we not connected.
Maybe he's jumping in for somebody else because he's the last one in line. You know?
Yeah.
Maybe he should hold on.
That's true, because the Zoom session is ready. There's everybody that's joined the Zoom sessions, but today it seems good. Tu l'as envoyé bien, non?
Ouais.
So you answer this mail then?
Yeah. Giving him the link.
He has a phone call. Can I call it? Hmm?
Le marathon.
S'organise alors, je pense.
Just wait like 5
Wait a
minutes.
So thanks for being patient. So we send him an email again. He asked for the link. So let's wait some, 2-3 minutes if he can answer the mail or sees the mail and can log in to the Zoom. So he doesn't answer the phone as well. So maybe he's already on mute because of his duty now.
Didn't want to present.
No, because it's
So
a
he
PhD student of this guy who sent the email. So they're different people already.
so maybe he's like died. Well, if not, we can just finish the session.
Well, normally the session is still ongoing. We can wait 2 minutes. Because if he show up,
Is it possible to be connected in remote or not?
Yes, so there's a Zoom link, but obviously he didn't get it.
yeah, but it's
You already got some reply?
yeah, but someone called Nikos Panapopoulos who should present.
So one of the other authors should present, obviously.
He sent you an email this morning? Maybe there is a matter of time difference between Greece and here, maybe?
I have no
Could be an hour, yes. Yeah. I don't know. I think we might have to close the session then if we don't get him connected. So this puts us in a position to be the first in line for lunch, which is not too bad then. But yeah, thanks again from my side to the presenters, and sorry for.
Maybe suggestion.
Yes.
Mr. Chairman.
Yes.
Maybe someone in the room
Might jump in.
something. Do you have any material to share with the rest of the community?
So now is the chance for doing.
Are you ready for 20 minutes? No? But why not? I mean,
Once in a lifetime opportunity, more or less.
okay, that's life. But you lose the opportunity, frankly speaking.
Okay then. Thanks once again, and sorry for that. And so I close the session.